we're going to talk about some of the cool features that Java 8 provides. And then next, this will just be about Java 8 in terms of its cool features. And then the next class probably will start talking about Java 8 concurrency features, because there's a whole bunch of new things that come along in Java 8. In order to make any sense out of Java 8, you have to understand a little bit about functional programming. Has anybody here ever programmed with functional programming languages? Great. OK. So then we'll talk a little bit about the functional programming paradigm. That'll be review for most of you. And we'll talk about some of the features that Java 8 provides. This particular talk, we'll talk about lambda expressions, functional interfaces, and method and constructor references. And then later we'll add in the other stuff that comes with the concurrency portions, which are streams, or more concurrent streams, parallel streams rather, and completable futures. If you take a look here, you'll see a nice little article that talks about some of this stuff in more detail. There's a lot of good things online. If you really want to understand Java 8, though, I strongly recommend you get this book. This is called Java 8 in Action, not to be confused with Java 8 in Action, which would mean it didn't do anything. It was inactive. But this is really a very well-written book. I've read it over and over and over again, and it really got me to understand what Java 8 is all about. And then we're going to show how these features are applied in this set of stuff. We're going to show how we're going to take our thread join test program that I showed you earlier when we were just talking about Java threads, and we talked about join and start and new and all this stuff. And then we're going to show how to rewrite that program using Java 8, and that's kind of fun. And you can take a look here at this in this Git repository to find the code that we'll talk about. All right, so let's first talk about functional programming. So functional programming has its roots in a mathematical paradigm called lambda calculus, and that's why they use lambdas. That's where the name lambdas came from. And basically, it's kind of funny if you look at this thing historically. So for many years, people wrote programs using functions. A good example of something that used functions would be a language like Fortran. It's been around since the late 50s, early 60s. And so everybody did things based on functions. So things like mathematical libraries were good examples of early computer abstractions, right? Function abstractions. And the idea there was you'd pass your parameters and into the function. It would do the computation. It would return a result. And then for a long time, like 30 years, we moved towards object-oriented programming. And the idea, as we'll see in a second, of objects is to kind of encapsulate the data within these classes, and then you expose methods to update and access the data. So that was the new paradigm. But there's always been this notion of functions as the main way of programming. So what's happened now, for a variety of reasons, is that this has sort of made a resurgence, this approach. And the basic idea is that computations are treated as the evaluation of mathematical functions. And in its purest form, which Java 8 is not a purist form, but in its purest form, the only things you can do is you can pass parameters as input to a function. It does computation, and it produces an output. And then those things can be chained together. So this is an example of a typical functional programming model where you have some input that comes from somewhere. You apply a function on that input. The function then produces output. That output is provided as input to another function. That then produces output. And then that produces input to another function, which produces output. So basically, it's f of x and g of f of x and h of g of f of x. And so you kind of chain these things together. That's the basic idea at a high level behind functional programming. One of the observations that follows from this, or one of the properties that follows from this, is the notion of not having mutable data and not changing state. So the idea is to try to avoid side effects that modify state. Now this seems a little bit wacky at first, and it is a little bit wacky at some level, but that's the basic idea. And we'll talk about ways that Java supports that, and sometimes ways you have to work around some of the obvious restrictions of doing things in this way. So you can see here that everything is done purely as functions on the input, and it produces an output. So there's no side effects on data per se in this approach. Why are side effects a troubling issue? What is the thing about side effects that make them tricky when it comes to computer programming? Why do the functional programming people feel so passionately about avoiding side effects?
You can't really see them if you're like in a function signature, or if you easily add
so they're sort of invisible, exactly. But why is that hard? What's the thing? It's hard to analyze your code. It's hard to look at the code and be able to say with any sense of certainty what its behavior will be. So there's a correctness dimension to this thing. It's harder to show the correctness of the code if you have side effects. That's number one. Anything else that has the downside?
Perhaps for concurrency.
Yes, and what is the perhaps? What's the thing?
So if you have side effects like reading and writing to like a variable and you don't have the correct synchronization mechanisms, then there's going to be race conditions.
Exactly. So all the stuff we just talked about last time about those synchronizers and protecting state and making sure things are visible and atomic and ordered and all this kind of stuff, those are all hard things to reason about. And the minute you start having side effects, in other words, you start changing state in multiple threads, then problems occur. So those are the reasons why functional programming avoids side effects, because it's easier to reason about, both from just a correctness point of view as well as from a concurrency point of view. Conversely, the object-oriented paradigm, which is more or less what you've been taught, hopefully, since you showed up here, because it's still a good paradigm, employs hierarchical data abstraction. So data really shows up as a first-class citizen here, but more importantly, hiding data is important. And even more importantly than that, it's hiding data in a hierarchical way. So here's an example where you might have, the use of inheritance. That's the funny symbols here, where we have an iterator, and then we have different kinds of iterators, and the state of those different iterators is hidden within a common interface that's inherited from some base abstraction or base interface. So the primary way of structuring programs in an object-oriented approach is to use classes and objects which are designed or are hopefully going to be stable. In other words, they don't change a whole lot, so you can have things that are fixed and fairly common. And giving those things more preference in the design methodology than the actions or the functions that are performed. Functions are subsidiary to structure. Structure is what really influences things. That's what's called an architectural viewpoint. Well, if you think about this for a second, that seems a bit at odds with what functional programming is about, right? Functional programming is about functions by its very nature, and object-oriented programming, although it's a little less clear from the name, is about structure. It's always thought it was funny, it's called object-oriented. It really should be called class-oriented because it's really about classes, not so much objects. So those are how those things differ. And moreover, in an object-oriented view of the world, the state is encapsulated by methods that perform so-called imperative statements. Imperative says, do this, do that. It's directions, it's commands, it's instructions. So here's a simple example where we have some data objects, trees, and visitors, and we iterate over them using the iterator pattern, and we go ahead and we visit each node in the tree and accept a visitor. And all the state is all hidden here. You don't see the state, but there's state that's being manipulated as these algorithms are running. So if object-oriented programming is largely about imperative commands on hidden data, functional programming is more of a declarative paradigm. And what that means is that you program by saying what you want to have done and not so much how to do it. Now we'll see that object-oriented programming has a bit of that as well, and that's one reason why they actually fit together quite nicely, like peanut butter and chocolate in a Reese's peanut butter cup, right? Each is tasty on its own, but when you put them together, it's this very powerful, tasty treat. Here's a little diagram, it's kind of like a flow chart that shows you, or a decision tree that shows you these different models and how they map to things. So we've got programming, which is how you talk to computers to tell them what to do. And we've got declarative programming, which is about the how, or about the what, not the how. And there are examples of things like Prolog, which is logic programming. There's functional programming like Haskell and Erlang and so on. And then we have imperative programming. We have procedural programming, which is Fortran and C, and object-oriented programming, which is C++ and Java. Now, imperative programming, on the other hand, in contrast to declarative programming, focuses on how a program operates via statements that change its state. And of course, we like to abstract those things, and that's what object-oriented programming is all about, not exposing implementation details, but it's still ultimately about making commands to get things done. Okay, any questions about those distinctions? With the extremes, like small talk versus, Haskell or ML. Those are sort of at the extremes, object-oriented, purely object-oriented with small talk, purely functional like ML or Haskell. And we'll see that Java 8 is actually a hybrid. It mixes both paradigms. So it's kind of like the Sphinx, right? It's the body of a lion and the head of a man or something like that, right? So it combines these things together. And the nice thing about this is it helps to reduce the gap that otherwise exists between business logic, which is what you want to have done in terms of requirements, and the computations you have to write in order to do it. And that Java 8 in Action book has lots of really cool examples that really make it clear, here's how you do it in classic object-oriented way of designing your code. Here's how you do it with the functional programming way of designing your code. Wow, the functional programming approach is so much cleaner and simpler once you understand what it's trying to do. However, that doesn't mean that object-oriented programming is useless. It just means that it's used for a slightly different purpose. And this is one of the reasons why I particularly like Java 8, because a lot of the pure functional programming languages don't pay any attention to structure. So as a result, you have these impossibly hard to understand functions that nobody can make any sense out of. And so it's very difficult to understand what the code does. It's very difficult to reuse it. It's very difficult to extend it. And you tend to write messy code that gets locked into what you originally did. So in some sense, Java 8 is the Reese's peanut butter cup of programming because it combines the best of both worlds. So you can use objects and classes and inheritance and all this good stuff to deal with the structural parts of your program, which are very important. And then when you need to do computation, you can write the computations with the Java 8 functional programming features. And as you'll see, because we're going to look at a lot of examples starting today, once you get your head around this, it's really, really cool. And the code is actually quite easy to understand once you have learned how to read functional code, which you may already have done. So in order for this magic to work, you obviously have to install Java 8, and there's the place to go to find Java 8 stuff. OK, let's now talk about some of the core features: lambda expressions, functional interfaces, and method and constructor references. Probably the single most publicized new feature that's been added to Java 8 is something called a lambda, or a lambda expression. This has also been added to C++. So C++ 11 has something very much like this. Java has something like this. They're different, but they're more or less the same idea. So a lambda expression is basically an unnamed block of code, like this. We'll see this in more detail, which could or could not have parameters. It's up to you, depending on what you're doing it. And this code can be passed as a parameter or stored in a variable and then executed later when it's needed. Now, why is this a win? Well, the main reason it's a win is because it helps to minimize or remove. Elide is a fancy name that means omit or remove. Verbosity, by focusing on the computation to perform and not getting lost in all the syntax. So if you're familiar with inner classes, here's how you would write an inner class to make a new thread that prints hello world. So you'd have to put all this scaffolding around: new, runnable, open, close, open curly brace, public void run, open, close, paren, open curly brace. Finally, you do the code you want to do, plus some more syntax. A lot of extra stuff. In contrast, with a lambda, you just say new thread, open, close, arrow, and you just put in the code you want to have done. So we looked at this before, just a little recap. Yeah?
What if you want to write additional methods inside the lambda class?
I'm sorry, you want to do it?
If you want to write additional methods in the lambda class in addition to run, like...
Oh, yeah. Great question. So what you can do in that particular case, if you want to have other methods, then you'd have to define a class that implements runnable, and then you could implement the methods in there. That's how you do it. So this works very well for so-called functional interfaces, and we'll see what a functional interface is. A functional interface is basically an interface or a class that has a single method that's abstract. And I'll show you some examples. So you could also do that as well. So here we go. A functional interface contains only one abstract method. Does anybody know what the significance of the diagram here is? Whenever possible, I like to try to put images on my slides that have some inner subtle meaning so that people can learn with like their right brain as they're learning left brain stuff. Does anybody know what is this? What kind of car is it? It's a Toyota Highlander. Does anybody know why that's relevant? They can only be one. That's right. So if there's a movie series called The Highlander, and it's kind of like what are these magical beings that fight with each other, and there can only be one. So there can only be one abstract method, just like there can only be one Highlander. So there's a bunch of different kinds of functional interfaces. I think there are 5 of them, and we're going to talk about them all, and I'll show you simple examples to make the points concrete. So the first kind of functional interface is called a predicate, and it is used to perform a test that returns either true or false. Here's what the interface looks like abstractly. And when you first see this stuff, it's like, what the heck is going on? But it's actually really cool. So somewhere there's an interface called predicate, which is parameterized by type t. And predicate has a single method called test. And test takes an instance of type t and returns a Boolean. OK, that's what that looks like. Here now is an example of passing a lambda in the context where a predicate is expected. All right, you ready for this? So we create ourselves a new list of integer, and we do that by making, we call arrays.asList, and we give 1, 2, 3, 4, 5. That's the list of values we want converted into a list of integer, right? So this is a list of integer. And then we go ahead and print out the list. And then we say, hey, list, remove anything that matches this predicate. And what this does, of course, is this says, for every integer I, which is in the list, we'll talk about how that gets there in a second. This is what's called type deduction. For every integer I that's in the list from the beginning to the end, check to see if I modded by 2 equals 0. That's just a computer science geeky way of determining whether something's even by modding it by 2, and if it returns 0, it was even number because there's no remainder, right? So this thing here is a lambda expression, and this lambda expression happens to match the predicate interface. So even though you don't see test anywhere, this is the code that performs the test, because it's going to take an integer I, which is this guy, of type t, which is what the predicate is up there. And then here's the actual implementation of test, and this returns a Boolean. So this will then go ahead and remove anything in the list that is even. And so when we print the list out again, then it only prints 1, 3, and 5. OK, any questions about that? When I first saw this, my head exploded, because I'm like, where's the method test? I don't see the method test anywhere. And the answer is, this is defining an anonymous block of code, an unnamed block of code. And this piece of code goes here as the implementation of the test method. This is the test method from the point of view of the predicate. The other question is, where the heck does I come from? And what type is it? Well, I is actually an integer. In fact, I could have written this as open paren integer space I close paren arrow. But with Java 8's type deduction mechanism, it's able to figure out the type of I. So I is simply one of the elements that's in the list, and that's just the way it works. You just have to get your head around this. It's really mysterious at first. It looks like a syntax error.
So
yeah?
If you were to say that I write like a test case which is doing some float operations and checking a range for float values, it will automatically deduct that it's a float?
I mean, assuming that it's in the right context, yes. Yeah. Yes, you could call it index or element or whatever you want to call it, as long as it doesn't have a conflict with another name. Yeah. All right, so that's a predicate. You'll get used to this crazy syntax after a while. At first, it's really bizarre, but it gets better as you go through it. All right, let's take a look at another example. This is one of the most common functional interfaces. It's called the function. Of course, function. So this function is going to apply a computation on one parameter, this parameter, and it'll return a single result. So function is a parameterized type of type t and type r, r being the return and t being the parameter type that's passed in. And it's as if there's a method named apply. So apply is the method that is going to be used when you have functional interfaces. So check this one out. This is kind of a fun one. So we're going to go ahead and make a list of threads, and we're going to have 3 threads with names of the 3 stooges, just because that's a good number of names of short names for 3 things, Larry, Curly, and Moe. So we have a list of threads. We're then going to go ahead and print out the threads, and it'll just print out sort of the fact that there are 3 threads with those names. And then what we're going to do, notice that these are not sorted. We're then going to go ahead and sort this list. We're going to say threads.sort, and we're going to tell it to compare using the name of each thread. So that's what we're going to use as the comparator. Now this actually shows a whole pile of things here. It shows this particular thing here is going to be a functional interface. It's going to be used to compare these things. And this method, this thing here is actually called a method reference. So this says to go ahead and compare these things, and it uses the apply. This method here will be used in order to get the function to do this. And then we go ahead and print the results out when we're done, so it'll then be sorted. There's another functional interface called a consumer. And a consumer accepts a parameter and returns no result. So unlike a function that returned a result, a consumer just goes ahead and accepts a result. So here's an example just to illustrate this. This is kind of fun. So over here we said system.out println for the threads. Over here what we're going to do is the same example, except now we're going to say threads.forEach system.out println. And so what this is used for, system.out : println, this is used as a consumer for the forEach method. And so what this does is for each thread in this list of threads, it will call this consumer function. And that takes the thread string to print, and it doesn't return a value. So that's printing out each of the threads using for each. So that's an example of a consumer. Then there's something called a supplier. And a supplier is a functional interface that takes no parameters and returns a value. So here's a somewhat contrived example. I had to look long and hard to find one that I could show that used the stuff that you'd find in Java on like 4 lines of code. So here we're going to make ourselves a hash map. And the hash map is going to be a map of string to string. So we have demon, which is naughty, and an angel, which is nice. So that's going to be the elements in here. And so we're then going to go ahead and put a name in here, like demon or angel or something else. And then we're going to go ahead and we're going to look up the person's name in the map. So we're going to go look up whatever name is, demon, angel, or something else. And we're going to get back something that's called an optional. An optional is a new Java 8 class that either contains a value or not. So it can be used for things that may or may not actually have a valid result. So here, when we look up the person in the map, if it's demon or angel, we'll get naughty or nice. But if we look up, Sam or something, it'll say, I don't know anything about Sam. So it'll actually return a null, and that gets stored here in the optional. And then down here, we're going to go ahead and say the disposition of the person is, and we're going to use a special method called or else get. And what or else get does is it checks to see whether the optional is non-null, and if it is, it returns whatever the optional's value is, like naughty or nice. But if optional is null, you give it something to return, in which case you're going to simply return the string unknown. So that's actually a supplier. That's a supplier that's just going to return the string unknown. So this will either say the disposition of the person is naughty, nice, or unknown. So that's an example of a supplier. Yeah?
So why should it be a supplier instead of just a value?
Because that's what the or else get method expects. It expects to get a supplier, something that will give it a value. That's just what the signature is. So we had to give it a supplier.
Also, what is so with the new hash map thing, you just put something in like curly braces inside that? Is that?
Yes, this is basically this is an initializer list for a hash map. So these are called the double. This is called the double curly brace approach to initialize things. I don't normally use that. I just wanted to have something that would fit on the slide.
Does it only happen for hash maps?
No, you can use it for basically anything.
So in the initializer or whatever, you can use the object methods.
Mm-hmm.
Okay.
Yes. Yep. That's another Java 8 thing. And then the final thing in here is something called a bifunctional. And bifunctional is used, it's much like a function, except it takes two parameters, a t and a u, which is kind of like left or right, or first and second, or whatever. So this is a pretty fun example. So we're going to have a map of strings to integers, which we call the IQ map. And we're going to give everybody in the Three Stooges an IQ of 100. So that's the name and the integer value for each of these things. And then we're going to decide we're being overly generous. So we're going to come in to the IQ map, and we're going to replace everything. And what this is saying is, for each element in the map that's the key and the value pair, go ahead and replace the value of each of these things with the current value minus 50. So now they have an IQ, they all have an IQ of 50. So that's probably more like the real IQ of the Stooges. So this is pretty cool because this is showing a bidirectional function that's used to do this. Here is how you would write the equivalent code if you were using Java 7. So what you would do is you would iterate through the IQ map for every entry in the map. And for each entry, you would set the value by taking the current value of the entry and subtracting 50. So this verbose code is replaced with this much more concise Java 8 Lambda code. OK, any questions? If this stuff doesn't sink in the first time you see it, don't worry. It takes a while to really absorb what the heck's going on, because it's so concise, and it's just throwing away all the extra stuff that you don't need. And it's letting the compiler do a lot of the work for you. OK, so this kind of goes back to your question from before. A functional interface can also contain one or more default methods or static methods. Actually, it can contain 0 or more. It doesn't have to contain any of them. But if you want to, you can put other things that are not abstract methods. Do you guys remember what is an abstract method in Java? If you have an interface or... Right. So great example is class runnable, or sorry, interface runnable in Java. Interface runnable has one method called run. That's a functional interface. It's got one method, and it's an abstract method. However, with Java 8, interfaces can now have not only static methods, which they always could have, but they can also have something called default methods, which is also completely wacky and crazy. So here's an example. There's a class called comparator in Java, and it's got a method called compare, and that's the abstract method. And then it's also got a default method called reversed. It's got a static method called reverse order. So this is an example of an interface that's a functional interface, but it actually has multiple methods in it. It's just that reversed and reverse order are default and static methods, respectively. However, you'll notice something else interesting, too, if you look carefully. There's also a method in comparator called equals, which is abstract. How the heck does this match with the rule that a functional interface can only have one abstract method? Well, the designers of Java left a little special case, which says any methods inherited from class object are not counted against the rule that you can only have one abstract method. So equals is inherited from Java lang object, so it doesn't count. So this is still a functional interface, even though it has multiple abstract methods, because the other abstract method it has is inherited from Java object. Yeah.
So why is that even useful?
Why is what useful?
Boolean equals.
Well, that's how you compare. That's how you compare two things.
Inherited from the object.
Yes.
So all objects will have that anyways, including.
Exactly. That's right. So I was just pointing out that there's other things in comparator besides compare. There's multiple, actually there's other things that are also inherited from Java Lang object. So if you take a look at the comparator interface, you'll see what it's got defined it. Since a functional interface only has one abstract method, you can omit the name of the method. This is why they only have one. That's why they only allow one abstract method, because they want to be able to have anonymous calls that can map unambiguously to the one and only method that's used to implement this stuff. So here's a simple example. So we've got a string array with a bunch of names in it. And now we want to go ahead and we want to sort this array. So here's how you would have sorted this array with the old way of doing things. So you say sort arrays.sort string array, this guy, new comparator string. I might be able to leave out the string here. Compare string I1, string I2, I1.compare to I2. You return that. That's the old way of doing things. But that's an awful lot of code. That's carpal tunnel syndrome inducing. So instead, the new way to do things with lambdas is to simply use this approach. And this is a functional, bifunctional interface where you're going to take S1 and S2, which are just any two strings in the array, and you're going to compare S1 to S2. So notice what we're doing is we're just kind of pulling out the part of the code here and just replacing it there. So we're just taking out the business logic and using it directly as an anonymous function. Notice that we don't have a name here. This method is not given a name. It's anonymous. It's a lambda. All right, so those are the 5 key functional interfaces. So predicate, function, supplier, consumer, and bifunctional. Those are the 5 built-in functional interfaces. Then there's also some other things that kind of build up from this that are really, really helpful, especially when you start using the streams framework. And they are what are called method references. So a method reference is a lambda expression that gives you a more concise way of identifying a particular method to use instead of having to write out the more verbose lambda expression. Lambda expressions aren't very verbose, but this is even more concise. So this is for people with even more carpal tunnel syndrome. So here's how you can compare all these elements ignoring case. So this is how you would have done it before. You would have gone ahead and made a new comparator whose compare method would have used the toLowerCase method to do the comparisons. And here's how you do this with a method reference. So you say arrays.sort string array string : compare to ignore case. So I think you'll agree with me that if you had to read a lot of Java code, you would much prefer to read that code once you knew what it meant than that code. This code is hard to follow. It's verbose. You can make mistakes just by typing the wrong stuff. Syntax errors, if nothing else. Here it's just like sort this string array with the compare to ignore case method. Boom. It's really simple. Now, for those of you who are familiar with C++ and C, what does this look like? It looks like a pointer to a function, right? Yeah, so that's basically what it is. So method references are basically glorified pointers to functions. A method reference can also be a handle to a constructor. This is a little bit more wacky example, but it illustrates the point. So here we have a class called constructor reference demo, CRDemo, and we create ourselves a supplier which is going to store a reference to the constructor in the supplier. And then we say system.out println supplier.get, because the supplier has a get method. And that will go ahead, this get call will call new, which will make ourselves a new CRDemo object, upon which we then call the hello method, and the hello method just prints hello. So basically, this get call makes a new element by using the constructor reference. That's not the world's most profound example of constructor references, but I wanted something really simple that didn't require a lot of other explanation to tell the story. Okay, so those are some of the basic building blocks. And in just a couple minutes, we'll do the quiz, but I wanted to at least give you an overview of the next topic, because what I just talked about up to this point is just to kind of get you in the right mental framework to understand what's about to happen. What's about to happen is we're going to talk about one of the most useful features in Java 8, which are called streams. Yeah?
What if you had a method named new?
You can't have a method named new. It's basically a reserved word.
Okay.
So sequential streams, we're going to talk about sequential streams first, and later we'll talk about parallel streams, support functional operations on a sequence of elements that are conceptually unbounded. I mean, eventually you're going to run out of memory, but you'll see very quickly you can have things that are unbounded. And so this is basically much like what we looked at before. It's a stream of processing that applies functions to transform the stream and then passes the result to the next function in the stream. Each operation or function in a stream runs sequentially, one after another, in the thread of the caller. That's for sequential streams. If you want parallel streams, it's a slight tweak to the syntax, and then things run concurrently. So here's a very simple example. First, we'll use an external iterator to show something. So here's a case where we're going to have an array of strings, and we want to go through this array of strings. So we take this string array, we turn it into a list of strings, and then we're going to go through every element here, and for each element I, we're going to replace the element in the array to replace WashU with Vanderbilt as the domain name. So let's say I had a bunch of old files that were stored at my WashU account, and I want to replace them with my Vanderbilt account. So that's what that's doing, right? So pretty straightforward. We're iterating through here. We're replacing each item from 0 to 2 by getting it and then replacing it. That's the old way of doing things. Here's the new way of doing things. We say stream, which is a class, of URL array. What that does is that converts URL array into a stream, and then the stream starts doling the thing out one at a time. And then for every element in the stream, which are these strings, we're going to go ahead and replace, for each string, this substring with this substring. And then we go ahead and we collect the results of this mapping into a list and store it here. So this is how we did this transformation before. Here's how we do it using streams. This uses an internal iterator as opposed to an external iterator. We'll talk more about those in a little bit, maybe next time. So what we're doing here is we're iterating through each element in the input data structure, the list. We're transforming each element, and then we're creating a result, and we're storing the result somewhere. And that is a teeny-weeny example of the power of streams, because you can start to put things together in a very cool way. Like iterators, each element in a stream, elements in a stream are visited just once during its lifetime. So it starts at the beginning and goes to the end, and then you have to make a new stream if you want to do some more processing or transformation. Here's one reason why this is so cool. Let's say I don't want to have a list of strings, but I want to have a list of URLs instead, or URIs instead, rather. All right, I take it back, URLs. So here's all I have to do in order to make that work. I simply throw in a new function that's going to transform each string that comes out of this guy to a URL. So URL : new is a constructor reference that takes a string and returns a URL corresponding to that string. And now I end up with a list of URLs. And all I have to do is just add this line in here. I don't have to change anything else, because it's all part of the transformation process. Rethrow function is just a utility function or method that converts a checked exception into a runtime exception. So the way to think about streams, to compare and contrast them with other things that you're familiar with, like collections, is a stream is something like a streaming video that streams the content, like Netflix or Hulu or something, whereas a collection is more like a DVD, where everything is stored in one place. So with a collection, it's all there to start out with, and you can then read and write to it. With a stream, conceptually, it flows, and it generates stuff, just like a stream of video stream or a music stream, audio stream, or something like that. OK, any questions about any of those things? And you can convert collections to streams via the .stream and .parallel stream methods. So this is probably a good place to stop, because it's quiz time. Next time, when we start up on Monday, I'll go through some really cool examples that show how to use streams to do more powerful things. And then that'll start segueing into the next programming assignments.